Problem M11, which is the combustion with caffeine. So the question says, the stimulant in coffee and tea is caffeine, a substance of molar mass 194 grams per mole. When 0.376 grams of caffeine was burned, 0.682 grams of carbon dioxide, 0.174 grams of water, and 0.110 grams of nitrogen were formed. Despite the empirical and molecular formulas of caffeine, write the equation for the combustion. Alright, so first of all, to get started, we're going to get the moles and the grams of each of the elements besides oxygen, because that's the one that's unknown. So in whatever equation we have with the combustion of caffeine and O2 on this side, and then the arrow, we have carbon dioxide, water, and nitrogen on the other side. So since we do not know this O2 over here on the left side, we're going to solve for all the other ones and then use those to balance the equation and find the mass of oxygen. So to start off, we have 0.682 grams of carbon. Grams of carbon dioxide. Alright, so using the molar mass of carbon dioxide, which is 1 mole carbon dioxide per 44.01 grams of carbon dioxide. That's the molar mass of carbon dioxide. And then we're going to use the mole ratio of carbon to carbon dioxide. And in the equation CO2, as you can see, when we have 1 mole of CO2, we have 1 mole of carbon and 2 moles of oxygen. So the molar ratio over here is just 1 mole of carbon to 1 mole of CO2. Alright, so we keep going. And this is going to cancel out gram CO2, and then we have mole CO2, that cancels out as well. So we're left with how many moles of CO2, which when you calculate it out, it becomes 0.0155 moles C. And we're going to use this number over here, obviously, to calculate the grams of carbon. So, going back to this number, which is the moles of carbon, we're going to multiply that by how many grams per mole, because we want mole on the bottom to cancel out with this mole. So 12.01 grams per 1 mole carbon. That's the molar mass of carbon, so cancel out the moles, and we are left with this many grams of carbon. Alright, so that part is pretty straightforward. So we're going to do that for the rest of the other two compounds. So for H2O, same thing, 1 mole H2O, which is, if you look on the periodic table and add up the molar mass of 2 hydrogens and an oxygen atom, becomes 18.02 grams H2O. And over here, this is where you have to make sure to pay attention to the molar ratio, because in 1 mole of H2O over here, we have 1 mole of oxygen, but we have 2 moles of hydrogen, hence the H2. So we have to make sure we do 2 moles hydrogen per 1 mole H2O. And that gives us this number when you calculate it out. Alright, and so on. So we go to the next step, which is using that number to find the grams. If you look on your periodic table, the molar mass of hydrogen is 1.0079 grams per 1 mole These cancel out, the moles cancel out, and we are left with about the same grams of hydrogen, because the molar mass is relatively zero, so we should expect that the grams and the moles are relatively the same. And for nitrogen, we have 1 mole of N2, 28.02 grams of N2, and 2 moles nitrogen, 1 mole N2. Because when we have 1 mole of N2, we have 2 nitrogen, so hence the molar ratio. So these cancel out, these cancel out, and we go to this number over here. It's the number of moles nitrogen. We use that. The next step over here, moles nitrogen times the molar mass of nitrogen. If you look on your periodic table, is about 14.01 grams. Cancel out the moles, and we are left with this many grams of nitrogen. Alright, so as I mentioned at the beginning of the video, we can solve for all these 3 different elements, how many grams there are on. So here's our equation, first of all. So we have caffeine. We don't know what caffeine is. It's some combination of carbon, hydrogen, nitrogen, oxygen, and we have O2 because this is a combustion reaction. On the other side, we have carbon dioxide, and water, because this is the simple form. This is the simple form of a combustion reaction. So, and in this case, we also have nitrogen, is what it said. So nitrogen was formed. All right. So right now we have how many grams of C we have, how many grams of H we have, and how many grams of N we have. And we know that this whole right side of the equation, let's see here, all of these 3 compounds put together are going to equal a certain number. And then when you subtract the individual elements from it, so the mass of carbon, the mass of hydrogen, and the mass of nitrogen, we should be left with the mass of oxygen. So we have these 3, and that's the one we're missing. So if we add all these 3 together, let's see what we get. Okay, sorry, one second. Backtracking my thought. Okay, I apologize. So we okay, so that's correct. We have found the mass of carbon, the mass of hydrogen, and the mass of nitrogen, and all these 3 elements are present in caffeine. So basically, sorry, one sec. Hey, can you guys be quiet for a second? I'm recording a chemistry video. Oh, sorry, no worries. Alright, sorry about that. So when we have the mass of carbon, hydrogen, and nitrogen, we can find the mass of oxygen present on this side, because these 3 elements, carbon, hydrogen, and nitrogen, are all present in caffeine. And by law of conservation of mass in an equation, we know that we're going to have the same amount of mass on this side as this side of the equation, given its the parameters are in a closed environment and so on. So when we add these three together, we should get the difference in the mass of each side of the equation, which is equal to this oxygen. So we go back to the mass of caffeine that the equation gives us. The problem gives us is 0.376 grams of caffeine. And then we subtract all of these values that we solved for over here in the carbon, hydrogen, and nitrogen. So all of these should equal let's add them all together in parentheses. Okay, and this gives us mass of oxygen, which is equal to 0.061 grams of oxygen. And using this number, we can go back to moles. Sorry, it was a little lopsided. 1 mole for every 16 grams. And this gives us that many moles of oxygen. Now, using the moles, since we're trying to find the empirical formula, we use all the moles. So make sure not to use the grams, but the moles. So let's compare. So we have that many moles of oxygen. I'm getting this number from over here, back from the top. This many moles of carbon. For hydrogen, we have that many moles of hydrogen. And for N, we have that many moles of nitrogen. And when we're trying to solve for the empirical formula, we always divide by the least number of moles, which in this case is oxygen. So when we divide oxygen into carbon, let's see what we get. Okay, we get about 4. And whenever we're dealing with empirical formulas, it's not going to be exact, but as long as it's not too far off, like 0.3 off, then we're within reasonable doubt to call this 4. So in this case, it's okay to call it 4. If it was 4.3, for instance, we might have to go to a different coefficient because that 0.3 could translate into a whole different empirical formula. So onward, oxygen to hydrogen. It's about 5. Oxygen to nitrogen is about 2. And oxygen to oxygen is just 1, obviously. Okay, so right there, these are our, that can be translated into the empirical formula.